So we're going to talk about how we can actually use RISC-V, the RISC-V architecture, extensions being developed within the RISC-V architecture for the automotive marketplace. Let's start with a few trends within the automotive marketplace. We're familiar with the fact that electrification is little by little happening. We have, of course, autonomous driving. We have things such as connectivity. Connectivity within the car is changing. And all of those things, those very high-level functions, are driving actually changes within architecture of systems within the car. There is increased computing requirements. You know, the day where your radio was your only electronics, those days are way behind us. There is more and more software in cars. You know, a Ford F-150 now is said to have more than 150 million lines of code, you know, more code than there used to be within the space shuttle. At the same time, we're going toward a world where car manufacturers want to differentiate the products using software. They want to use software in order to collect fees. We are talking about here about software-defined vehicles. There'll be levels of performances in the cars based upon software. There's already something which is happening. However, at the same time, safety remains something fundamental. It's actually in the standards, it's actually in the regulations. Safety is not going to go away anytime soon. It's fundamental. Security is becoming one of those requirements that over time are going to match the level of requirements that we see from safety. And actually, you know, when we look into safety versus security, when we have security built in, it's actually easier to implement some safety functions. At the same time, and this is a trend that was started by Tesla, among other things, there's going to be a consolidation of compute resources. There is, not so long ago, there was 150 ECUs within a car. We're going to see consolidation of those ECUs between going from discrete ECU to domain controllers to zone controllers, just as we kind of see on that diagram here on the right. At the same time, standardization is going to be very important. It's going to be standardization at the level of requirements such as safety, such as security. It's also standardization within the brands of a car manufacturer. Car manufacturers may own multiple different brands. They will want some level of standardization of the underlying hardware platform between all the brands in order to optimize the costs. So we're dealing here with electronic engines that over time, because we have this consolidation of requirements, need to handle multiple types of requirements. We are going to see some systems that are going to need to handle very high safety processors that are controlled by standards such as ASIL-D. And well, when you have to do an ASIL-D processor, this is actually something expensive. There are certification requirements, so it's hard, it's difficult, it takes time, it takes a lot of money, it takes a lot of resources. When you handle safety, if you try to break everything down in multiple SOCs, well, the bill of material goes up. That's expensive, okay? So that's an issue. And so here, what little by little we are actually considering, and this is where the RISC-V ISA is going to help us, is how can we, within one single chipset, mix tasks which have different level of requirements when it comes to safety and security. So, kind of underlying what we just talked about. On the left, let's take an SoC which has a safety island. That's the case where you basically have two processors. You have one which is actually certified to the level of ASIL-D, and one which is certified to the level of ASIL-B. Two processors, you certify one for one level, the other one for the other level. You kind of integrate everything. And it works, okay? You can make it happen, all right? And then here, another option, and this is where the RISC-V ISA will help us, is, well, let's have within one system, one CPU, so to speak, various levels of requirements which are handled and protected from each other through isolation. So we will have, for example, a safety RTOS on top of a secure monitor, an hypervisor, and we will handle ASIL-D tasks. At the same time, on top of a RTOS, we will handle other tasks, ASIL-B tasks. But as we discussed earlier, well, we need to make sure that those ASIL-D tasks do not impact the functions of ASIL-B, but most important, vice versa, that ASIL-B tasks can't impact what's happening with ASIL-D tasks. And then we can have some other regular tasks of a regular execution environment. So we need to be able to share one system between all these tasks. We need to be able to isolate the tasks from each other. We need to be able to protect the memory from each other. We need to be able to protect the tasks from each other. So, we need to be able to handle software failures. If there is a software failure here in an ASIL-B task, we want to make sure that it's not going to impact ASIL-D. So we don't really want to design this whole chipset to the ASIL-D requirement. That would be expensive. That would be a lot of work, all right? Yes, it would be feasible, but that would be a lot of work. That would be expensive. So let's see how we can then meet the requirements of ASIL-D, ASIL-B, and regular tasks with the RISC-V ISA. Now, we need to understand what the standards requires, what ISO 26262 actually defines as isolation from interferences between the various tasks. So fundamentally, you need to make sure that when there's a failure within one environment, let's say the regular execution environment or an ASIL-B environment, that this doesn't cascade within the other environments, such as, for example, an ASIL-D environment. So that's timing and execution, it's memory, it's exchange of information. We need to take all those things into consideration, the timing, the memory, and the information which is processed within the various systems. So there are a few things that we can do. We can use the RISC-V ISA to achieve those objectives. Let's assume that we have an RTOS, a CPU, which is a real-time CPU. It has some security firmware. It has a safety RTOS. And on top of this RTOS, we have some tasks, which are either ASIL-D or B, or just regular, no specific requirements. So in this example here, the RTOS would have to actually be ASIL-D certified, because you have here an ASIL-D task running on top of this RTOS. So that pass here, that needs to actually be ASIL-D certified. But if we can, let's make sure that we don't have to also force an ASIL-D certification on top of the other tasks. So what we do is we use PMP, the PMP architecture, in order to protect the security firmware. Then from there, we know that, for example, an RTOS usually does not use an MMU to partition the memory. We use the extension, the SPMP extension. That SPMP extension actually delivers functions which are very similar, equivalent to an MPU. So we can then isolate memory between the various tasks. We can deliver that level of isolation that enables us to actually meet the requirements of ASIL-D versus ASIL-B versus a regular execution environment. We get that static partition from the security firmware, which operates here as an hypervisor. Okay? So I hope you can see the graph well enough. An example of SPMP usage is that in the case of an RTOS environment, you would have a task. It has some data. It has some code. But then at some point in time, you need to switch to another task. All right? We go from an SLB to an SLD, for example. So that task is preempted. There is an increase in privilege. Then the RTOS code takes over with its data, its stack, and then a second task comes and takes over. So memory here has been purged, and the other stack comes in with its own set of data and its own code. All right? And SPMP is a set of extensions that actually allows for that. So now let's look at other things. Let's look at how we use hypervisors. So we have various modes of execution within RISC-V core. And those modes, as you probably are very familiar, are machine mode, supervisor mode, virtual supervisor mode, and virtual user mode. Now, you can use those extensions with either an MMU for full virtualization or with SPMP for static partitioning with the hypervisor. So in that case, we would have something that looks like that. We would have a real-time hypervisor on top of the security firmware, and we would have a SLD task running on top of that real-time hypervisor. Then on top of the real-time hypervisor, we have a safety RTOS with SLB task and then a rich execution environment. And the SPMP enables us to offer partitioning between those various environments. So the requirement here, not unlike what we discussed earlier, is that the hypervisor needs to actually be SLD certified, okay? The SLD task runs directly on that hypervisor, right? The safety RTOS, which would have lower level of certification, only SLB, would run on top of the hypervisor and would have its own tasks. And then, of course, we have the partitioning of the rich execution environment all the way on the right. So SPMP allows for protection between those various OS. That's the primary objective of this extension. And it protects the various tasks that operate within those execution environments and meets those requirements of protection of memory, of protection of data, protection of the timing of execution, protection of exchange of information. So, when we consider, if we were to summarize a little bit what we've been discussing here, is security versus safety. We're talking here about security features that actually enable us to implement safety functions. All right? The objective of security is to protect against attacks, and the objective of safety is to actually tolerate faults. All right? And we use here some security mechanisms to prevent cascading effects of a fault in one system from impacting programs in another system. So this techniques of isolations is actually something which is quite common, used in multiple systems. It's based, of course, on the level of certification of an hypervisor, of a system which is going to split various execution environments. And we could see through the diagrams that that hypervisor always needs to have the highest level of certification. In this case, this was SLD. So in summary, we have now architecture modifications, architecture features that allow us to aggregate functions within one SoC, whereas in the past we may have considered multiple SoCs in order to split a function which needs to be SOD versus another one SOB versus another one just regular execution environment. With those extensions, we actually have the underlying security mechanisms that allow us to integrate everything within one chipset. And we facilitate our work from a development point of view, a maintenance point of view, a certification point of view, and of course, very important, from a bill of material point of view. So those functions offer great advantages. Those extensions offer great advantages to the developer within the automotive market. So that's the objective of this presentation, is to advertise those SPMP extensions to developers in the RISC-V community. Okay? Questions?
The hardware has to be SOD or CPU.
You have the extensions. You don't necessarily have to have the whole hardware SOD. Okay? What is really important is to have actually your security firmware and your hypervisor. Okay? Do you need to actually systematically qualify everything all the way to the hardware to SOD? Not sure. I'm not sure of that. Okay? What you need to have is your hypervisor, which is going to perform those isolation functions, SOD certified. Okay?
So hardware can be ASIL-QM or has to be ASIL-B or anything?
No, it doesn't necessarily need to be any one of those things. Okay?
Generic hardware.
Right, it can be generic hardware. It's absolutely true. Okay? All right? And you will find that in other environments, okay? This is not, strictly something which is about, automotive systems, and ISO 262, you can have generic hardware, but if your hypervisor on top of that is at a certain level of evaluation, for example, you would take common criteria evaluation level, 5 or 6, then you can run applications on top of that will be protected underneath the certification level of that hypervisor. Okay? All right? But you will have a certain number of underlying hardware requirements. Okay? You will, for example, have requirements such as you will have a secure boot, a root of trust, and things like that. You will have requirements on your memory management systems. Okay? And here, the SPMP extensions will help you with that. Okay? All right? Other questions? So it's going to be here some software. Those models, those examples we were discussing, that's software, okay? But that hypervisor, to achieve that level of certification, is going to have a certain number of requirements. Your security firmware is going to have requirements, and your hypervisor is going to have requirements. Okay, you're going to need a root of trust to secure boot. You're going to need a partitioning mechanism for your memory, with some underlying features that include hardware and things like that. Okay, all the details a little bit above my level of technical skills. All right. Okay. Yeah. Other questions? Very good. All right. Thank you.